Ray Cox was 33 years old. He had had a tumor removed from his back the previous month. He was lying face down on the table at the East Texas Cancer Center in Tyler, waiting for what was supposed to be a routine follow-up dose, 540 rads, to a small patch of tissue between his shoulder blades. What he received was somewhere between 16,000 and 25,000 rads. The intercom crackled. He told the technician he was burning. The technician thought he meant the air conditioning. This is what the investigators eventually found. Between June 1985 and January 1987, a single model of radiation therapy machine, built by a Crown Corporation of the Canadian government, delivered massive overdoses to at least 6 patients in 5 hospitals. 3 of them died. It was not a mechanical failure. It was not radiation that escaped containment. It was software. Software that the manufacturer had inherited from a previous model, written by a single programmer who no longer worked at the company. A programmer the manufacturer could no longer find. The Therac-25 was a linear accelerator, a LINAC. It produced a beam of high-energy electrons that doctors directed into tumors. The machine could operate in 2 modes. In electron mode, the beam went straight to the patient at energies up to 25 megavolts, useful for shallow tumors near the skin. In X-ray mode, the same beam was first fired through a thick metal plate inside the machine, called a spreader or beam flattener, which converted the electrons into photons. X-rays, useful for tumors deep inside the body. The critical detail was the spreader plate. When the machine was in electron mode, the plate had to be physically retracted out of the beam path. When in X-ray mode, it had to be physically inserted. The plate moved on a mechanical assembly that took just under 8 seconds to complete its journey from one position to the other. If the spreader plate was in the wrong position when the beam fired, the patient received a dose orders of magnitude higher than intended. The Therac-25 had 2 predecessors. The Therac-6, built in 1972. The Therac-20 in 1976. Both used the same dual-mode design. Both had 3 independent hardware interlocks, mechanical switches and micro-switches that confirmed the spreader plate's actual physical position before the beam was allowed to fire. In 1982, when AECL released the Therac-25, they removed all 3. They removed them because the software, they argued, already verified the spreader plate's position. A hardware interlock was redundant. It cost roughly $3,000 per unit to manufacture. The Therac-25 was a linear accelerator, a LINAC. It produced a beam of high-energy electrons that doctors directed into tumors. The machine could operate in 2 modes. In electron mode, the beam went straight to the patient at energies up to 25 megavolts, useful for shallow tumors near the skin. In X-ray mode, the same beam was first fired through a thick metal plate inside the machine, called a spreader, or beam flattener, which converted the electrons into photons. X-rays, useful for tumors deep inside the body. The critical detail was the spreader plate. When the machine was in electron mode, the plate had to be physically retracted out of the beam path. When in X-ray mode, it had to be physically inserted. The plate moved on a mechanical assembly that took just under 8 seconds to complete its journey from one position to the other. If the spreader plate was in the wrong position when the beam fired, the patient received a dose orders of magnitude higher than intended. The Therac-25 had 2 predecessors. The Therac-6, built in 1972, the Therac-20 in 1976. Both used the same dual-mode design. Both had 3 independent hardware interlocks, mechanical switches and micro-switches that confirmed the spreader plate's actual physical position before the beam was allowed to fire. In 1982, when AECL released the Therac-25, they removed all 3. They removed them because the software, they argued, already verified the spreader plate's position. A hardware interlock was redundant. It cost roughly $3,000 per unit to manufacture. The Therac-25's control software ran on a PDP-11 minicomputer. It had been written for the Therac-6 in the early 1970s, adapted for the Therac-20 in 1976, and then ported to the Therac-25 in the early 1980s. By the time it reached the Therac-25, the code had been through 3 architectural generations. No formal documentation existed. There was no test suite. There was no source control. There was no design specification that an engineer outside AECL could read. The code had been maintained for many years by a single programmer. By 1985, that programmer had left the company. AECL could not locate him to ask questions about how specific subroutines worked. The software did 2 things relevant to this story. First, when an operator selected a treatment mode at the console, the software queued a command to move the spreader plate. The plate began moving. While it moved, the operator was allowed to continue entering parameters, energy level, dose, duration, anatomical site. Second, before firing the beam, the software checked an internal variable, a single byte. If that byte equaled 0, the system was ready. If it was anything else, the system would refuse to fire and display an error message. Here is where the bug lived. That byte was incremented every time the operator edited a parameter. After 256 edits, it wrapped around back to 0. So if the operator was working through a long shift, slowly accumulating edits across many patients, eventually that byte returned to 0, and the system declared itself ready, regardless of whether the spreader plate was actually in position. But that wasn't the only bug. The Therac-25 had been operating in 5 hospitals for nearly 3 years before the first serious injury. In June 1985, a woman called Catherine Yabra was being treated for breast cancer at Kennestone Regional Hospital in Marietta, Georgia. Her prescribed dose was approximately 200 rads in low-energy electron mode. She was burned, visibly, severely. The hospital reported it to AECL. AECL responded that the machine was incapable of delivering such a dose. They did not open an investigation. 3 weeks later, the same thing happened to a 66-year-old woman in Hamilton, Ontario. Same machine, different unit, same result. AECL still did not investigate. It took until March of 1986, 9 months and 3 more incidents later, for the second bug to be found, the race condition. At the East Texas Cancer Center in Tyler, technician Mary Beth fed the patient's parameters into the console. She selected X-ray mode. The spreader plate began its slow 8-second movement into position. Then she realized she had selected the wrong mode for this patient. She cursored back up, changed it to electron mode, then back to X-ray, then reconfirmed the energy. She did this in less than 8 seconds. When she pressed B for beam, the system fired. The software, in those 8 seconds, had registered a mode change, then a second mode change, but had not waited for the plate movement to complete and reset. An internal flag called Class 3 got into a state the software's authors had never anticipated. The system believed the spreader plate was in X-ray position. It was not. It was still mid-motion, somewhere between the 2 end stops. The beam fired at full electron energy, 25 megavolts, no conversion, direct, unfiltered. Into Voin Ray Cox is back. He survived the first appointment. He came back 3 weeks later for what should have been the next session. The same operator, the same machine, the same edit pattern. He died on September 1st, 1986. The reason this kept happening for nearly 2 years was not that the bug was undiscoverable. It is that the people who could have discovered it were not believed. After Voin Cox died, the East Texas Cancer Center had a problem. AECL had told them the machine could not have hurt the patient. So either AECL was wrong, or 2 people, who Tyler had irradiated with the same operator using the same machine, had developed coincidental radiation burns from nothing. The medical physicist at Tyler was a man called Fritz Hager. Hager went into the radiation room. Alone, he sat at the console. He pressed the same 5 buttons in the same order, X, edit, E, edit, X, beam, as fast as he could. He did this dozens of times over 2 days, with dosimeters placed where a patient's body would have been. On one of those attempts, he reproduced Malfunction 54. The same error message both patients' operator had seen. He measured the dose. The beam was firing at full electron energy. The spreader plate was retracted. The machine could not have hurt the patient, AECL had said, but it had. Hager could now show it. He phoned AECL with the exact reproduction steps. AECL took 11 days to acknowledge. In the meantime, the Therac-25 in Tyler stayed in clinical use. Other Therac-25s elsewhere, in Yakima, Washington, in 2 other U.S. sites, in 5 Canadian hospitals, also stayed in clinical use. AECL eventually issued what it called a corrective action letter in July 1986. It instructed hospitals to remove the up arrow key from the keyboard, to prevent operators from quickly editing parameters. The actual race condition was not addressed. In January 1987, the Therac-25 in Yakima killed another patient. Different bug, the byte overflow this time. Same root cause, no hardware interlocks, software-only safety, no testing for edge conditions. Only then did the FDA force a full recall. The Therac-25 was withdrawn from clinical use in May 1987. 3 patients had died directly, 2 more had been permanently mutilated and lost full use of limbs or face. 1 patient's death is sometimes attributed to underlying cancer, but the radiation burns made her terminal years intolerable, and the timing was post-overdose. AECL redesigned the machine with 3 hardware interlocks reinstalled. They reintroduced log files that could not be cleared. They added an internal watchdog timer that physically disabled the beam if the software stopped responding for more than 400 milliseconds. The total number of the Therac-25 units that had ever been manufactured was 11. In 1993, a software engineer named Nancy Lehv-Sun published a paper titled An Investigation of the Therac-25 Accidents. It became the most cited reference in software safety engineering. Every undergraduate computer science program that teaches software ethics or critical systems references this paper. The phrase Therac-25 now means, what happens when you remove the hardware safety net and trust the software alone? There is a quiet pattern in 2026 that should worry people who know this story. The FDA has approved over 800 algorithms classified as artificial intelligence as a medical device since 2017. Many of them make safety-critical decisions: which images get reviewed first, which dose gets calculated, which patient gets triaged. In a significant fraction of these approvals, the regulator does not see the source code. The hardware interlock, the physical mechanism that says, if the software is wrong, this cannot happen, is gone, because the decision being made is informational. There is no plate to physically insert or retract. This is the structure that allowed the Therac-25 to operate for 2 years with a known reproducible bug. We covered a related pattern in case 001, the Iberian blackout, a regulation drafted but unenforced. 5 years instead of 2. Same failure mode, different industry. Link below if you missed it. The free case file for this video documents 3 current medical devices that share the Therac pattern. Link in the description. Every failure leaves evidence. We follow the trail. The next case opens on Thursday. A structural failure photographed, documented, and flagged years before it killed 114 people in a hotel